Begin by dragging the CFX Fluid Flow module
into the project workspace
and right click on Geometry and open a new Design Modeler geometry. I'm going to sketch on the ZX plane, so select the negative y-axis and then select Z and X. So I'm just going to zoom in on this region here because that's where we're going to be sketching. And I'm going to start by selecting our computational domain. So we're just going to create a rectangle. I'm just going to make it coincident about the origin, just so it helps me determine where everything's positioned. The domain is 20 meters long and 10 meters high. So we can assign those dimensions here. And the next thing we need to do is create the shelter that's going to sit somewhere in the middle here. So the shelter is a relatively simple construction. Just going to use another rectangle that's coincident with this axis to create the back wall. I'm going to leave it thicker than it needs to be, just so it's easy to select that line in a moment. And I'm going to say that it's 2.5 meters tall and 3 centimeters deep. We then need to create the roof, which is the thing that we're going to be varying. Select another rectangle. I'm going to begin this roof as being a rectangle coincident about that rear point. And again, just dragging it to some approximate size and not being too concerned about the exact sizing, because we can always modify that with dimensions here. So I'm going to begin with a thickness dimension of 3 centimeters again. And then I'm going to just modify that width to be 0.25 meters. And again, we are going to increase this and see what the effect of wetting is on the ground beneath the shelter. So I'm going to tick this box here, and what this will do is it will make this dimension something we vary. So I'm going to call it, in this case, roof width. So when we run the simulation, we'll repeat the simulation multiple times and vary that width by values that we've chosen. So I'm going to extrude this domain, but before I do that I need to get rid of any internal lines. So for example, this line needs to go. And there should actually be 2 there. One from the top rectangle, one from the lower rectangle. And the same down here. There should be 2 lines, one from the overall domain and one from this rectangle here. I'm then going to extrude this computational domain, and I'm just going to extrude it by 1 meter. So we've got a unit width value of wetting. And as you can see, that shape is now cut out in our extrusion. So rain is going to be coming from left to right. It's going to be striking this building, and the flow is going to be causing it to recirculate. And what we're interested in is how wet this area underneath here becomes. So what I'm going to do is create a sketch on the bottom face of the domain.
The reason I'm doing this is so we've got an area beneath the shelter where we can calculate the amount of rainfall that falls on it.
So I'm just creating a sketch on the XY plane. So this is the plane that the shape sits on. And I'm just going to slightly rotate so I don't accidentally select the top face here. So I'm just going to create another rectangle, coincident about that axis. and I'm going to make it 1 meter wide because the domain is 1 meter wide. I'm going to make it 1.5 meters long. So that one there, and this one here. So that should remain 1 meter, and this should be 1.5. So just for our calculations later, this area is going to be 1.5 meters squared. We're going to use that extrude tool again, but this time we're not concerned about making a three-dimensional shape. We just want to create a surface here that's differentiated from this surface or this surface on the ground. And the way we do that is, rather than selecting add material, we use this tool imprint faces. Once we hit generate, just make it so that I can select this face here, and then I can select this face that's under that shelter there. So now we can perform wetting calculations on this area and see how effective the width of that shelter's roof is. So once you've done that, just shut down Design Modeler. In order to effectively model the flow around this shelter, I'm going to need to refine the mesh quite close to it. So I'm going to right click on Mesh, Insert and Sizing, and I'm going to select all of the faces in this region here. So I need to use Box Select, and I just need to drag so that those faces are selected. And then in geometry that's picked them up there. I'm going to reduce the element size down to 3 centimeters for the moment. I may refine that further. And I'm going to change the growth rate to be 1.1. So that just means that the cells will move from this size here to this free stream size slower. I'm also going to change the global element size to be 0.3 meters, and what that will do is mean we've got a slower transition from these larger cells to these smaller cells. I'm also going to change the quality option, so we want to smooth the mesh down to a target skewness of 0.85 and increase the smoothing. This will give us a better quality mesh and hopefully a better solution. We also need to include prism layer cells. So if you right click on Mesh, Insert and Inflation, the geometry we're interested in is the fluid body, so it's this entire domain here. And the boundaries we want to apply these prism layer cells on are all of these lower fluid boundaries. So that's the ground, that's the shelter, that's that special part of the ground where we're measuring the rainfall. I'm going to change the inflation option to be total thickness and just give that 5mm value. And just running this, we can have a look at how our mesh is set up. So that looks quite good to me. We've got relatively small cells away from the geometry, and then in the region close we are relatively fine. I may just decrease the growth rate on the face sizing, and that just will ensure that this region here has slightly smaller cells so the flow gradients are properly captured. So that certainly looks better. So when you're ready, just shut meshing and right click on Mesh and Update. And once your mesh is finished updating, just double click on Setup. So you can see our computational domain, and in this case we've got flow coming in from left to right. So we're going to begin by double clicking on Default Domain, and we're going to modify some of the basic settings here. So in this box, just select Fluid 1 and delete it, and then create two. One called Air, and then the next called Rain. By default, the fluid material is going to be air. So if you just select the rain on this box here, you should be able to just select water. And then it asks what type of fluid it is. In this case, we're going to treat it as a particle transport solid. And we're going to just select this dimension here to be 0.002 meters. We're also going to include buoyancy in this case, because of course rain falls through air, and our gravitational acceleration is acting in the negative z direction. And I'm going to take the density of air as our reference density. So if we apply that and move to our next tab, I'm going to leave this as an isothermal case. I'm going to leave this model as k epsilon, and I'm going to ignore the influence of buoyancy turbulence because these particles are so small. I'm going to assume that there's no rough wall behaviour and there's no erosion happening. In terms of the fluid pair models, the most important setting is going to be this one here. So in a fully coupled simulation, the air would influence the particle movement and the particle movement will influence the air. Whereas in this case, we're going to choose one-way coupling, so only the wind influences the rain particle and not the other way around. There's a couple of options here for determining drag force on the particle. You can read through the documentation, have a look at each one, but I'm just going to select a drag coefficient of 0.5. And we have the option here to inject particles at different regions. That's not really appropriate for our case because we're going to be specifying them on the boundaries, but if you wanted to specify them to come in there, for example, you could. So we're now going to create the boundaries where the flow is going to come in, leave, and of course stagnate. So creating our first boundary, I'm going to call that inlet, and that's going to be located at this wall on the left here. And I'm going to say that the air has a velocity of 1 meter per second. And in this case, rain is going to be entering the domain. I'm going to set it to enter at the same speed as the air. And I'm going to say that we have 1500 particles coming in at a mass flow rate of 1.5 kilograms per second. So if we choose our diameters to be 0.002 meters, we can then insert another boundary. In this case, I'm going to call it sky, and that's going to be an opening boundary condition. So it's going to allow the flow to leave, but also to recirculate, and it's going to be that surface there. So the relative pressure is going to be 0, but there is going to be some particle coming in. And what I'm going to do is change this normal speed to be Cartesian velocity components. So they are going to have a velocity of 1 meter per second. That's going to be the same as the inlet. But what I am going to do is also create a small negative velocity in the z direction. So that just means they enter the domain and don't have any difficulty crossing that. I'm going to say that we've got 3000 particles coming in with a mass flow rate of 3 kilograms per second. And again, just specifying some diameter. So what you'll find in CFX is some of these settings override each other. So I'm putting all of the settings in, and we're just going to treat this as giving us some number of particles. So we now need to create the outlet. So in this case outlet, and that will be acting of course on this rear face over here. So we'll need to select and rotate. And in our case we're just selecting that relative pressure again, and we're not concerned about any particles entering the domain. I'm just going to change this to an opening boundary condition so flow can recirculate. We've got a 0 relative pressure, and we're not considering any rain flow to come in from the outlet. We've got several more boundaries we need to specify. So the next one is going to be ground. And I'm going to treat that as a wall, and it's going to be this boundary here and this boundary here. And it's a no slip wall. I'm just going to set these restitution coefficients to be 0 so that when the fluid impacts upon them it has 0 velocity, so it effectively sticks. This is a bit of an assumption in the sense that it's not going to be considering rain to splash, but otherwise we'll end up in a sea of parameters and we'll probably not get something useful out of the model. I'm going to create the next boundary and call it ground wet. And this boundary here is also going to be a wall, and it's going to be that part that we specially created. Same restitution coefficients as the previous boundary. These side walls here are going to be created as symmetry boundary conditions. So in this case it would be this wall and this back one here. And there should only be one boundary remaining, and that's going to be the shelter. So I'm just going to right click, rename, and call it shelter. I'm just checking that the fluid values are the same as the other walls. Just applying those. And we just need to go into solver control. I'm going to keep these iterations relatively low because we need to do parameter sweeps. So we need to get through these simulations fairly quickly. Just keep them at 100. I'm going to change the local timescale factor to be 0.3. So we're trying to force these to converge quite quickly. Again, we're not striving for accuracy here, we're just demonstrating a process. And if we go to particle tracking, we can determine when our particles stop being simulated, so how far the tracks go on for, and I'm going to change that to be 50 meters. So what you'll find sometimes with particles, they come into a domain and then they just stop. And that's because the solver has been told to stop creating them. In our case, we're not going to let that happen. So once you've done that,
now you can shut down CFX Pre.
And just double clicking on solution. So just selecting double precision, and because we've got quite a lot of cells in our domain, I'm going to parallelize this. And just setting that to run. So we'll run this simulation, then we'll do some analysis in CFD Post, and then we'll run a parameter sweep of this simulation. So once your simulation's finished, just double click on results to open up CFD Post, and then we'll begin our analysis. So I'm going to start just by creating a colour plane and selecting it to be placed on the ZX plane, and because we know that our domain is 1 meter wide, if we place that at 0.5 meters it will sit straight down the middle. And I'm just going to colour that initially with velocity magnitude. So scrolling up, selecting velocity. So you can see that there's a region of stagnation, a region of recirculation, and we've got some interference from the opening boundary condition there. And that's okay, it's far enough away from our geometry that it shouldn't matter too much. So we can also see the trajectories of the particles. So if you just tick this option on here, you can see that the particles are coming in and down. If you want to see more of the ones that we created, just double click on Res Particle Rain and change the max tracks. So obviously they're all going to follow a relatively similar pattern. What we can then do is create an expression, and I'm going to call it rain, and I'll call it M2. I just mean that to say rain per meter square. We're going to approximate how much rainfall is landing on that special part of the ground that we created. In this case I'm going to use the area average function. So I'm creating an area average, and then the variable I'm going to use to define this is going to be the rain average volume fraction. So it just means how much of the surface is going to be rain. In this case that water volume fraction. And just remember that our boundary was called ground wet. So you can either type it in, or you can just right click, select locations and then ground wet. And then you can also divide it by the area of ground wet, and that will just give you how wet it is per unit area. So if we just plot that, you'll get some value per meter squared. I'm going to right click on this expression and create it as a workbench output parameter. So we're going to repeat these simulations numerous times, and we're going to repeat them for different values of roof width. So here I'm going to change the width to be 0.5 meters, and I'm just going to keep increasing its size. I'm just going to extend that all the way up to 2 meters, and what it's going to give us is how much rain is falling on that bit that the shelter is supposed to be sheltering. Again, this is not going to be an exact how exactly much rain, but what it's going to do is show us a trend of rainfall behaviour. So I'm just going to select update all design points. So this simulation might take a while because it's relatively complex. So we'll just check back in after these simulations have run. So when you're happy, just select update all design points, update all. So our simulations have now finished running, and what you can see, just visually observing, is that we've got this negative trend of rainfall per meter squared with increasing length of canopy. And what we can do is just right click and export this as a CSV. So I've exported mine, I'm just going to open it up. So just viewing this data, so as we increase roof width, what you can see is that there's a massive fall off in rainfall on that area of protected ground per meter squared, which is what you'd expect. What we're also seeing though is not a linear trend, but certainly a significant fall off. There's a few things to note here. We are using an approximation of rainfall because obviously during a rain shower there are millions and millions of rain droplets falling. We've only approximated 3,000 or so. So in this case, it's very much an approximation, and use this as a trend finder rather than actual volume of water flow fallen.